Hello, Geometry Advanced students. So today we are going to begin Chapter 10, which is a unit on circles. So our objectives for the next few lessons are to identify the characteristics of circles, recognize chords and diameters of circles, and recognize special relationships between radii and chords. So before we get into too many specifics here, let's take a look at this picture. So if we are given that we have circle O and the radius is 12 and that segment AB is also 12, we also know that segment OP is perpendicular to AB, that's given to us in the picture. We want to find the length of segment OP. So if you're thinking about, what can I do to the picture? I would recommend drawing in radii since it says the radius is 12. Maybe let's draw one in from O to B and also O to A. So again, the radius is 12, so both of those segments are 12. If segment AB is 12 as well, we have, again, hopefully you notice, an isosceles triangle. So when a segment is drawn in perpendicular to the base, remember it bisects it. So if that segment AB is 12, that means AP and BP are both 6. So if I'm looking for OP, again, what I want to focus on is this right triangle here in yellow, or the other one. So if you remember when we did the previous chapter, I said this is going to keep coming back to us. So this is a 30, 60, 90. The reason I recognize that is because if this is 6 and that's 12, it's double it. So this is like your x side, this is like your 2x side. So OP would be your x root 3 side. So that means the length of OP is 6 root 3. So again, all those special right triangle concepts are going to keep coming back to us as we keep progressing. Okay, so let's continue on with our notes. So let's go over some definitions. I know we've talked about circles a little bit, but not in great depth. So a circle, by definition, is the set of all points in a plane that are a given distance from a given point. So again, that's the definition. All of the points on the circle here are the same distance from the center. Now you have your radius, which is defined to be a segment that joins the center to a point on the circle. And if you didn't already know it, the plural form of radius is radii. Remember, all the way across is your diameter. Okay. So continuing on, the picture on the right here, hopefully you notice, is a picture of concentric circles. If you have 2 or more coplanar circles that have the same center, so in my picture on the right, the center is A, and they have different radii, then they're going to be what we call considered to be concentric. Okay. And if 2 circles have congruent radii, then they are congruent. So if I were to prove that 2 circles were congruent, all I would have to do is prove that their radii are congruent. So like if 2 circles both have a radius of 5 inches, then they're going to be congruent because their radius, the length of the radius is the same. Okay. Let's go over some more definitions here. So if a point, or not if a point is inside or in the interior of a circle if its distance from the center is less than the radius. So for example, I is inside the circle because the distance from A, oops, didn't want to do that. So the distance from A to I is less than the radius. Okay, for the second part, a point is in the outside or in the exterior of a circle if the distance from the center is greater than the radius. So now, if I draw a segment from A to E, that's going to have a length that's greater than the radius of the circle. So therefore, point E is outside the circle. And then finally, a point is on the circle if make this work here. If a point is on the circle, if the radius, if its distance from the center is equal to the radius. So B would be on the circle because the length of AB is the radius of the circle. So 3 options. It's either inside, in the outside, or on the circle. Okay, a couple more definitions here. So we have a chord and a diameter. So a chord is a segment that joins any 2 points on the circle. So in this picture, CF, or segment CF, would be a chord because, again, it has endpoints on the circle, so segment CH. Another chord in the circle would be segment DR. And again, it has endpoints on the circle, and I wrote RR. That should be segment DR. Okay, now more specifically, we can say that segment DR is a diameter because a diameter is a chord that passes through the center. So again, my diameter would be segment DR because it goes through the center, which is point A. Okay, a couple more topics to cover here. So if we go back to that very beginning problem we looked at, we had a segment perpendicular to a chord that came from the center. So we have this definition. It says the distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. So if you're ever asked in a problem, well, what's the distance from the center to a chord? That's the length of that segment that's perpendicular to the chord. So in this case, it would be the length of segment AM. Okay, and we have a theorem about this. So it says if a radius is perpendicular to a chord, then it bisects the chord. Okay, so if we're given that we have circle A in this picture and that segment AD, here's that perpendicular, if AD is perpendicular to BC, then according to this theorem, then it bisects the chord. So segment AD would bisect segment BC. So again, if it's perpendicular to the chord, it's also going to bisect the chord. And again, it comes from the fact that if you draw on your radii, you have isosceles triangles. You could prove those triangles congruent and then get BM congruent to CM by CPCTC. Okay. Now, coming from the other direction, it says if a radius of a circle bisects a chord that is not its diameter, then it's perpendicular to the chord. So this is the converse of it. So this time, again, if I have circle A, if I know that AD bisects segment BC, then I can conclude that AD is perpendicular to BC. So again, that's that theorem kind of going hand in hand. If it's perpendicular to the chord, it bisects the chord. If it's going through the center and bisects the chord, then it's perpendicular to the chord. So again, it goes hand in hand. Okay, let's take a look at one more theorem here. So it says the perpendicular bisector of a chord passes through the center of the circle. So that's a statement. So if I want to write that as an if-then, as a conditional statement, I might say something like, if a line is the perpendicular bisector of the chord, then it passes through the center. So if I'm looking at my picture, I would be given that line DM is perpendicular to segment BC. So if line DM is the perpendicular bisector of the chord, then it passes through the center. So I would say my conclusion would be line DM passes through point A, because again, A is the center. So let's take a look at a few examples. We've done a lot of review of vocabulary here today. We haven't really done much with number crunching since the first problem. So like I said, let's take a look at a few examples. So if I look at the first one, it says find the distance from the center of a circle to a chord that is 10 millimeters long if the radius of the circle is 13 millimeters. So I'm going to draw a picture, and it would make sense to draw a picture of, guess what, a circle. So again, in the circle, we have a chord. So I'm going to draw a picture of a chord. Again, this chord here is 10 millimeters long. If the radius of the circle is 13 millimeters, we want to find the distance to the center. So the distance to the center would be like this perpendicular segment here. So remember, if it's perpendicular to the chord, it bisects the chord. So each of these pieces would then be 5. And if I know the radius is 13 millimeters, I want to draw in a radius here. So that's 13. So again, if I'm looking for the distance to the chord, thinking about your special right triangles, remember we have one with 5 and 13 in it. It goes 5, 12, 13. So the distance from the center is 12 millimeters. So again, those triples, those special right triangles are going to continue to show up. Even though you already tested over chapter 9. We're going to continue to use them as we progress. So again, a quick problem. Okay, let's take a look at one more example. This one has a couple different parts. So it says circle P touches or is tangent to the x-axis. And we know P has the coordinates of 15, 13, and Q has the coordinates of 19, 16. We want to find three things. We want to find the radius of circle P, we want to find the length of PQ, and the length of AB. Now, how this helps me, if you think about it, if it is tangent to the x-axis, okay, that length there would be the radius of the circle. So if P is at 15, 13, if I drop it straight down, this point would be 15, 0. So hopefully, if we think about it, you know, what's the radius of the circle? Hopefully you're saying that's 13. So for part A, the radius of circle P is 13. Okay, next, to find PQ. So let's erase this a little bit. So again, Q has the coordinates of 19, 16. Okay, and again, I want to find that length. So what we could do is use our distance formula if I want to find the length between them. So again, according to the distance formula, I'm going to take the square root. The difference of the x's squared, so 19 minus 15 squared, and then the differences of the y's. So it have 16 minus 13 squared. Okay, so 19 minus 15 is 4, so 4 squared plus 16 minus 13 is 3 squared. Okay, so that gives me 16 plus 9, which is 25, and the square root of 25 is 5. So this length is 5, and again we said the radius is 13. So next we want to find the length of segment AB. Well, again, my Pythagorean triples, we have one that says 5, 12, 13. So if QB is 12, AQ is also 12, so that tells me that AB has a length of 24. So again, dealing with circles, but bringing back all those right triangle concepts to us. Okay, so for your assignment today, you have, it's listed right here on the last page of your notes, page 443, numbers 5, 6, 8, 11, 12, 14, 16, and then 22 through 24. And as always, if you have questions, please let me know.